you everybody for joining us for a very exciting conversation here today. So we are talking with a couple of representatives for an exciting Michigan-based startup called, I guess, not necessarily Michigan-based, not a Michigan-based, mostly Michigan-based startup, BlueConduit, which I'll get into in just one second. But if you're here to talk about how machine learning is being used to identify lead service pipes, you are in the right place. So first and foremost, I want to introduce myself. I am Jacob Smith. I'm joined by my colleague, Ryan Robinson, who I don't know where she is on your screen, but she's somewhere. Wave to the people, Ryan. Hey. And we are here representing Collider, which is a community of tech innovators who are leveling up our skills while solving meaningful challenges together. So if that sounds like you, if you're looking to be leveling up your skills while solving meaningful challenges, we encourage you to connect with us in all the different ways that we'll drop in the chat here. And please don't be a stranger. We've got lots of other exciting stuff in store. Collider is a project of a company called Altimetric, which is a digital transformation company based here in Michigan. And we are very, very excited to kick off today's conversation. So as I mentioned, we're here chatting with representatives from BlueConduit. We've got Ian Robinson, Managing Director, and Jared Webb, a data scientist on the team. And again, they are using machine learning algorithms essentially to help governments improve efficiency when looking to replace lead service pipes that could potentially cause health risk. So all sorts of reasons here in Michigan. That's a particularly poignant conversation with the Flint Water Crisis, as well as ongoing issues we're experiencing in Detroit and elsewhere. But it's an issue that impacts folks all over the country. And we're so thankful to have innovators like the BlueConduit team who are working to address this important challenge. So without further ado, what I want to do is I want to go ahead and just dive right into the conversation. So to start, Ian, I was hoping that you could explain in your own words kind of what is your team at BlueConduit working on? What is the problem and how are you guys trying to address that problem?
Great. Well, thank you very much, Jacob and Ryan and the Collider team for this. We're really excited to be here. So as Jacob started explaining a bit, what we do at BlueConduit is we use machine learning to locate lead service lines. So lead service lines are the pipes that run underneath your lawn that connect the water main to your home. These can be made of different materials. They can be made of copper. They can be made of plastic. They can also be made of lead. And in the United States, there are 6 to 10 million of these lead pipes in service. And what happens is if you have a lead service line in your home, you increase the risk of having lead contaminated drinking water. So that is a public health crisis. And the fact that there are so many of these in the US remaining means that it is an emergency. But the question that is, why are we here talking about machine learning to locate these pipes? They're underground. Shouldn't you just be able to look and find them? It's not as easy as that, which is why we're here. There are the records that cities maintain about their pipe materials are either missing, they're old, they might be 80, 90 years old in note cards somewhere in City Hall. They might be wrong. You might have records that were written in the 50s and 60s, but nobody has updated them, so you have no idea what's going on. And to verify or check what the pipe material is a very expensive process because you have to dig a hole to find it. And so what we do at BlueConduit is we help cities better understand how many lead pipes they have and where in their system they might have lead pipes so they can prioritize their abatement and efforts and get the lead out of the ground as quickly as possible and as efficiently as possible.
Very, very cool. And so we're going to get into the specifics of what that looks like, what the challenge looks like in a bit more detail. But first and foremost, Ian, I was hoping you could dive into a bit of just how did this project start?
Yeah.
So I understand that this was born as a in response to the Flint Water Crisis. I was hoping you could explain kind of what the connection is there, and also, yeah, how did this project get off the ground?
Perfect. And I'll start, but I will let Jared then take over a bit because he was, I'll call him one of the protagonists in this story about using machine learning to locate the lead pipes. So in 2016, when the Flint Water Crisis received international news, it was clear, the experts had agreed that the lead service lines were the main source of lead contamination in the water in Flint. But there were two big questions, and so it was recognized that those pipes needed to get out of the ground. But in order to remove the lead pipes, you would need to have a budget to understand how many pipes would need replacing, and you would need to know which pipes, which homes you need to dig holes at, and which ones you don't need to dig them at, so you can get them out as quickly as you can. So that's the question. I'll let Jared talk about how, with a team of data science students from Michigan, he got involved and really how this took off.
Sure, thanks, Ian. Yeah, so I was actually leading a group of students at the University of Michigan called the Michigan Data Science Team. And we were students, we were trying to level up our data science skills. But we started out by doing just like Kaggle competitions, which I don't know if you've heard of Kaggle, but they're kind of boring. They don't have a lot of impact. And we knew that the Flint Water Crisis was happening. There was all this media attention, but we didn't think that it had anything to do with us until we had someone reach out to us from Flint saying, hey, can you help us understand what's going on? We don't have just a water crisis. We have an information crisis. We have no idea where these lead pipes are, and we don't know what to do about it. It's extremely expensive to dig a hole and find a copper pipe and then fill the hole in again. So I teamed up with, we started out as a big team, and we kind of, refined this into a research project where we worked together. We wrote a machine learning pipeline, and we worked with the city to gather data for that pipeline using representative samples of service line materials in the city. We sent people out to dig a few hundred holes instead of, there's 55,000 houses in Flint. We dug a few hundred little holes to see what the materials were to prime the pump on the models. And we eventually started working hand in hand very closely with the city and providing predictions for which houses had the highest probabilities of having lead pipes and which ones didn't. And the city, the team that was managing the project took that information and used that to prioritize resources for digging and replacement. And we had a pretty high hit rate. Hit rate is kind of our metric for success. How often do you actually find lead when you dig a hole looking for lead? And during this time, we were, between 80 and 90% of the time we were finding lead pipes. Things were going along well, and we took this and we wrote some research papers about it. And the city said, okay, well, you guys have done a great job, but we're going to bring on this big company to come manage the rest of the project. And this was at the end of 2017. And so we thought we were kind of done with it at this point. We provided all of the predictions to this big company, and we have saved emails. We reached out to them like 9 or 10 times saying, hey, we can help you find the lead, just let us know. Anyway, what ended up happening is in 2018, when the company took over, the hit rate went from 80% to 12%. The company was digging in exactly the wrong places to find lead. It seemed like they were finding lead on accident when they did. If you had asked us to take our predictions and design the worst way to do the program, it would have been pretty much what they ended up doing. And so the hit rate went down, and the NRDC, who we were working with at the time, the Natural Resources Defense Council, they were one of the stakeholders in managing these federal funds that were running the program. And they asked us to look into this, and we did, and we found this abysmal hit rate. The NRDC took our findings to court, actually, and a judge ordered the city to return to our model and use the predictions from the model to prioritize which houses you dig at, instead of whatever method they were using before. We don't really know. When the city switched its prioritization back to our methods, the hit rate went back up to 80%, and we found lead again. And yeah, and so that felt good. That, like, we were glad that the money that was going to Flint was being used to replace pipes and not to just dig holes, which is what everyone was. I mean, this is what was happening, is contractors were digging holes and filling them in again, and a lot of them made a lot of money doing that, but they weren't actually fixing the problem, right? So anyway, we once again kind of thought that we were done with the project after, for the second time. And then some journalists ended up writing about our story. The Atlantic wrote an article about it. And all of a sudden we started hearing from other cities saying, hey, can you do this here? And that is when we transitioned from a small research team doing things in our free time or for fun, like just as research. We weren't getting paid to do it. We realized that this was something that needed to go dispersed to the rest of the cities in the United States, at least, where this is a lurking problem. Flint was a canary in the coal mine. There's lead pipes everywhere, actually, and most places have not kept track of where they are. So the story since then has been one of trying to scale our technology and make it so that instead of just one person with a laptop emailing back and forth to the city, we have a highly controlled, measurable, overseeable process that can scale to, now we have cataloged, well, we're making predictions for more than 500,000 service lines at this point. We're probably close to 1 million. And we're bringing this to lots of new geographies and new settings.
So I was going to ask, and
yeah,
sorry, didn't mean to cut you off.
No, I was saying that's the story. Yeah.
To elaborate on just that last point you made. So to be clear, is Flint unique in its use of lead pipes, or like what, or is that something that you expect to find in all municipalities around the country? I mean, yeah.
So lead pipes become illegal for plumbing after 1986. So pretty much anything built after 1986, it's not going to have a lead pipe, probably, but actually it's once in a while you find one. And the lead pipes for plumbing goes back to the Romans. Like, it's such an excellent material for plumbing. In fact, plumbing is in lead on the periodic table is PB, and it's all around lead. The only issue is that lead is a neurotoxin, and that kind of throws a wrench in the whole problem in the idea. So lots of cities were using lead for plumbing and have used lead for plumbing for hundreds of years. And the reason that no one kept track of where the lead pipes were is, like, no one knew that it was actually a hazardous material and that it would create learning disabilities, and it's definitely linked to elevated levels of crime. People that grow up in a highly lead toxic environment they are hampered for the rest of their lives. But at the time, no one knew. So yeah, we find it in lots of places. And some of the areas of the United States, like new subdivisions, obviously don't have any lead pipes. But any older city, anywhere in the United States, I would expect that you would find some lead pipes for drinking water.
And so back to you, Ian. So thank you so much, Jared. That's amazing context. Really scary issues. So thank you for contextualizing that. So thankfully, you all are working to hopefully solve this, or do your part to help solve this. So Ian, question for you is, on the flip side, so you brought up the interesting point that the that larger company came in and had a misalignment of incentives where they were very inefficiently spending money because it was this inflated government contract and they don't really care, whatever the case may be. So you came on, as I understand it, to scale the business side of this project, taking it out of a student research project, et cetera. How do you ensure moving forward that you align profit with your social mission to avoid the incentive, the perverse incentive issue that you're describing with this other company? Oh, you're on mute. You're on mute.
Great. So I think thank you, Jacob. That's a great question. And there's a couple of ways we think about this. And interestingly, I think when you look at it, the incentives, first off, is the longer it takes to replace lead pipes, the greater the public health risk, the longer that residents live with the risk of pipes. And so it is, first off, a public health incentive and that cities and municipal utilities, because of them being municipal entities, are driven by that. But then you think about kind of where are the incentives in terms of money and otherwise that would incentivize somebody to make better decisions when it comes to replacing pipes. So first, if you are a municipal utility, your budgets are already stretched. Flint was an exceptional case in the sense that Congress allocated $100 million to replace those pipes. Most cities in the US do not just have a blank check of this is what I don't know how much money I'm going to need, but this is some amount and I'll find a way to spend all of this. And so there is an incentive, because if somebody isn't giving you that money from a large government grant in that way, who's going to pay for it are going to be taxpayers or ratepayers. And so you need to find a way to control costs for these projects that are going to cost tens of millions of dollars over or hundreds of millions of dollars for large cities over a 10-year, 20-year period. And so there is that. There's also, in kind of changing regulatory environment, which we don't have to get into all of the details, except to say that 2 points are: one, utilities are now more responsible to know and liable to know what the materials of pipes in their systems are made out of. They have to create an inventory and submit that to the government. And number two is, in certain states, including Michigan, utilities are required to replace 5% of their lead service lines per year for the next 20 years so that they get to 100%. The fewer digs that if a city needs to spend less money in terms of exploratory digs to get their pipes out of the ground, then they will not have to raise taxes. They won't have to make a rate case to increase that which are unpopular, as you might imagine, for residents. And so there's several different incentive structures there to ensure to make it so that utilities are incentivized to get these pipes out of the ground as efficiently as possible.
Got it. And then, not to hold your feet to the fire, but just because I'm curious, if you all do your job and all the service pipes get replaced, are you putting yourself out of business? And I guess maybe that's a question to save, because I'm curious to know what other applications the technology you're building has, which might be a better way to frame that question. So
I'd say that we want to put ourselves out of the business of finding lead pipes, because we want all the pipes to be found. I think of like that clearly, but there are enough other data science questions when it comes to infrastructure, when it comes to water, when it comes to public health, where prioritization, prediction, targeted data gathering matter, that we see there's plenty of opportunity once all the lead pipes are out of the ground, that will still be in business and still have a lot of interesting questions that we can do good solving.
Got it. Did you have something to add there, Jay?
All I was going to say is that I think the goal of any hazard mitigation company is to put themselves out of business, hopefully.
That's an interesting point. So thank you guys for diving into that. That's very, very interesting. I'm curious. So you had mentioned before we started the call here that so you've talked about how this data can help empower governments to prioritize the way that they're spending money digging for the pipes, finding the pipes. How about the public-facing side of the data question? So is there also data that's being made available to residents to help them better know, for example, if their house is at high risk of having lead pipes? I know that was a big issue with Flint, where folks just didn't know if their house was at risk.
So absolutely, I think one of our core values as a company, but also something we just believe, is that information around what the pipe material is going into your home or to your neighbors or your friends and loved ones' home is should be publicly available and accessible information. In Flint, for several years, this information of what the pipes were made of was being used to guide the replacement efforts. But we've also, in the last year, made it accessible to residents so that they can search for their address online, and they will understand what the pipe material is going to their homes. But really, what this is about is not just making the information available, but it's really making it accessible and actionable so that there isn't a sense of panic. So if you're in a community that is already stressed for how much money it has for replacement effort, just putting a map online with what the service lines are without giving residents anything actionable that they can do, it doesn't make it a good map for people in that way. And so I can share right now my screen. We have a public facing map online that is in for some maintenance right now, but this is an example of what we've built for Flint. The new, as I had talked about, the new regulations in Washington are actually forcing cities to make more accessible maps and inventories of their service lines. So this is a map that Jared made with folks from the NRDC, or similar to what was made, where it is every parcel in Flint is color coded based on whether the service line material is is non-lead, low likelihood, or known to be lead. And so you can search down and you click on a parcel, and then it tells you what the material is. It tells you what the previous material was. And then there's information about what to do in this case. And so you can do that. Accessibility is a key for us. So it's also got a colorblind friendly view in the color palette and the Spanish view as well. So making sure that these tools are available and accessible is one of the things that we really care about as a company, because decision support isn't just something that utilities need to use this information, but it's also something that residents need to use as they await replacement, so they know what they can do to reduce their possible exposure to lead.
And I would just add to that is that the more that the community feels invested and like they are able to participate and empowered by this information, the better it is for us. If there's a mistake in the record somewhere, or if someone got a replacement and the utility didn't write it down, if there's this ongoing conversation with the community, it leads to better data for our models, which can hopefully lead to better tools for the community, which can create a virtuous cycle.
That makes sense. So I'd love to dive now back to get Jared back involved and to get a bit more technical. So before we do that, I want to just remind everybody, please, and Sarah, I see your question in the chat here. Fantastic question that I'm going to work in just a moment. Please do drop questions in the chat. I'll work in as quickly as I can. This is really, we want to open this up, and I don't have a ton of background in machine learning or anything like that. So would love to hear from everybody to be helping me ask some more detailed questions here for Jared. We got the chief data scientist in the house, so please don't be shy. But in that spirit, Sarah here has a fantastic question about what data points are being used for determining the probability. So beside relative age, what other criteria might factor into that equation?
Sure, yeah. So basically anything that we can get, right, is what we want. Anything that describes the home. So we mentioned that Flint did not have any records indicating where the lead pipes were. That they eventually actually found some hand-drawn maps in a basement of a city building that were water damaged. And so a lot of them were like not, swaths of the map were not usable, but they did have some grad students, thank you grad students for doing tedious labor for for nothing for your research. Anyway, I've done it myself. So some grad students at Flint went through and digitized those records and made those available to us. Now, those records ended up being wrong about as often as they were right. However, that record becomes an input into our model. So it could be, yeah, the records are unreliable, but it could be that records combined with other information come together to make a prediction better. Okay, so any existing records, we include that as any assumptions that a utility might have, that is included in the model. Besides that, I see in the chat that someone mentioned age of home. That's a big one that we look at. There's lots of other information that we included. So any sort of parcel information that the state tracks for tax purposes, that goes in. So it's going to be not just how old the home is, but what's its assessed value, what kind of zoning is the building in, things such as that. We incorporated information from the American Community Survey, which is demographic information. So these are at kind of a coarser level than parcels, but it still ended up being useful and contributing more than other features, in fact, to the final predictions in the model. And then finally, I want to mention that there's a few other features that we crafted just out of strange data that the city handed over to us, and they weren't really sure if it would be useful. One was the location and the type of every fire hydrant in the city. So what we did is we had this map of fire hydrant types, and we calculated using Euclidean distance, just using latitude and longitude, the nearest fire hydrant type to every single home in the city. And that becomes an input into the model as well. And so all these came together, and that particular feature ended up being predictive. Like it wasn't like the most important feature in the model, but using each of the myriad ways of measuring how important a feature is to the final output, this consistently showed up in like the top 10, top 20 features. So yeah, anything, this is what we get in Flint. It's the same story. We kind of have to start from scratch in every single city we go to, where we have to say, okay, what do you got? And then it's this artisanal process of combining anything they have. We scour the internet for publicly available information, real estate records, anything like that, and then tie it all together and then put it into the pipeline.
Wow. And then great question in the chat here around just like the format of the data. That's a great one. You mentioned hand-drawn drawings and fire hydrant data. Like if a city gives you, the question's about digitizing the data. If a city gives you reams of paper records, how are you handling that? Are you processing it through language processing, or are you, how is that?
That's a good question.
Working?
Yeah,
so sending it to Fiverr.
Right. So these records, these paper records, were digitized by a team of GIS graduate students at Flint. And so they are, I want to give them all credit they are due. That was a huge task and really important for understanding the crisis at the time, and also ended up being an important feature in many of the models that we ran. So that's great. A lot of the parcel information is already digitized, and most cities have something like a GIS department. Now, this is kind of the story of the late 20th, early 21st century, as people were collecting data, digitizing all kinds of data, and then sitting on it. Like, what do you do with it now that you have it? So we were lucky that we didn't have to do much digitization. We have worked with some other partners since then in some other settings where we used OCR, that's optical character recognition, to extract text from paper records that had not been digitized yet. And that's typically, sometimes it's just, a word like letterbrass, but there may be other information that is extractable from natural language. Excuse me, sorry.
Wow.
Yeah, I see another question. I can just go through these questions. Someone's asking what kind of model we used. We didn't, so K-nearest neighbors, so the question is what kind of model is being used, KNN or classification. There are some limitations to k-nearest neighbors that mostly that's just not very performant for training. And then in the end, it doesn't perform as well. We used various classification algorithms. We tested a whole bunch of them. Any of you that have done data science before or data science competitions won't be surprised to know that the algorithm XGBoost, it's called Extreme Gradient Boosted Trees, performed the best. However, the performance is, I mean, it's the best, but it's like better by 2% or something over random forest, which is better than like 3% over logistic regression. The models are highly accurate. There's in fact a lot of signal in the noise here. And so the hard part is setting up the data correctly and making sure that you're training the model correctly. Once you've done all that hard work, feeding it into the model, it doesn't matter that much which model you use in this case. We're not doing like deep learning here. This isn't a neural network kind of problem. Excuse me again, sorry. But yeah, and I would say that in general, for most classification tasks, this is the case, where the hardest part is setting up and understanding the precise formulation of the problem. And the model that you use is going to be kind of a secondary question.
And so,
go ahead.
Yeah, curious to know, so in terms of determining the accuracy, so on the flip side of the data collection, the entity, if it's the government or whoever else who's actually doing the digging, is then reporting based on your recommendations, we dug here, and they're reporting back to you whether or not they found lead pipes, if I'm understanding that correctly?
Yeah.
How is that being digitally done? You know what I mean? Like how is that information being transferred back to you?
Inefficiently. So in the case of Flint, this is actually, this has to happen as part of the legal settlement that the judge ordered. So what that means is that the city has a lawyer who the city sends information to a lawyer who sends it to the NRDC lawyers who send it to me. And so it's like spreadsheets getting passed around, just horrible. We want to avoid that in the future as much as we can. But basically what happens is every few weeks I get an email saying, here's the newest data. And then I have to like hand put it back in. We've been kind of experimenting with a user facing product where maybe the cities we're working with can upload this data and have like a portal to just put it in and have it get automatically incorporated. Yeah, but basically, I mean, these predictions, the city is not making split-second decisions about where they're going. This is something that happens over the course of weeks. So it's not like we need a lightning fast pipeline here. The pace that they send us data is fine. And what we've been doing since Flint is we either have access to the geodatabase where whenever they update information, like we can just go every week or whenever we want and pull the most recent data, or they'll send database dumps to us and we'll incorporate them that way.
Got it.
Yeah, but it is, and then at that point we can measure accuracy. So we will, I mentioned hit rate before, but there's lots of different ways to measure accuracy. And this is related to another question that I'm seeing in the chat here. The question is, we want to make sure that we're not missing lead pipes. So in statistics, there's two concepts of accuracy that are kind of at odds with each other, and that's precision and recall. So a precision is a measurement of a hit rate. How often are you finding the thing that you're looking for? And then recall is measuring how much of the thing are you looking for you're finding. And usually you have to have a trade-off between those two things. Let me give an example to clarify this, because I know it's kind of an abstract idea. Excuse me. Imagine you have a medical test for testing for whether 100 people have cancer. You have 100 people and 5 of them have cancer. You could have one model where you choose the one person that has the highest probability of having cancer, and you get that right. Okay, that means that your hit rate is 100%, right? You found everyone that you looked for that had cancer has cancer, but there's 4 other people that you missed out on, right? So that's a low recall, high precision model. On the other hand, you could also just say that everybody has cancer. And then you would get the 5 people that have cancer, you would definitely get them, but there'd be 95 people that don't have cancer that you were wrong about. So yes, you found everyone that had cancer, but your model is not very precise. And so usually you have to kind of decide where you're comfortable on the spectrum between those 2 dumb approaches. And you can't often improve recall without sacrificing precision, and you can't often improve precision without sacrificing recall. So in our case, we want to be very, very conservative. We would much rather dig up some copper pipes and make sure that we get all of the lead pipes out of the ground. And so what we ended up doing was setting up, with our agreement with the city, a very, very low threshold, and saying anyone with a probability above this threshold, this very low threshold, is going to get their pipes inspected and then replaced if necessary for free. And then
that's presumably part of the reason it's an 80% hit rate, not a 100% hit rate, is because there's some percentage of that gap is the difference you're describing.
Exactly,
right?
Exactly. What do you do with a house? So you have maybe houses with like an 80, 90, 95% probability of having lead. And then you have houses with a 1 or 2%. What do you do with a house that's at 30%, right? So that's the question. Someone's asking what the recall rate is. That is a good question. Off the top of my head, I don't know the number, and it's kind of hard to say because pipes are still being replaced in Flint. And so out of the outstanding probabilities, out of the outstanding pipes, we haven't verified them yet. So I can't give the exact recall rate. I can say in simulation, recall is, if we choose that low threshold, then we typically have very high recall, 90% above in simulations, right? But we won't know the full story until we get every single pipe dug up in Flint.
And so another great question in the chat here from Mark. So given that the data set is all over the place and older, what do you do when there are like big pieces of missing information that you might be missing from one place but not another? How do you handle those gaps in the algorithm?
Yeah, it depends on what kind of data we're looking at, right? So there's, for example, categorical data, which is going to, this is something like, pick zoning, right? Every single house has a zoning category, and there's a handful of possible values that can go there. If that's missing, the very fact that it's missing may be informative. And in fact, for any kind of data, the fact that it's missing may be informative. And so one approach is to take any missing data and just fill it in with a placeholder value, say -1. And now the algorithm can say, okay, this is a label, this is a value that means something, and we can maybe learn from it. And so that's one approach, and that's the approach we take, by default for a lot of the categorical data that we have. And then you have data like year built, the year that the house is built. So the fact that is missing may be informative, and we do want to track that. But then again, if you have one house and all 7 of its neighbors were built in 1935, you can probably infer that this house was built around that time, maybe. And so that's an approach that you would take for this kind of numerical data. But that's the, this is very sophomoric. We'll say like this is not really fancy, sophisticated missing value imputation. But it's, it worked very well. By assigning these missing values a placeholder value, like the models improve, right? And we've been able to measure that.
That's great. One more question. So speaking of trade-offs, we hosted a talk recently exploring bias in AI models. And Ian, you and I had chatted about this a little bit when we were talking before. I guess I'm going to ask that question in an open way. Like, how do you mitigate bias in the data? You alluded to some sense of random sampling, so I'm hoping you could speak to that. Ian, you had mentioned that the actual data sets sometimes steer towards having better data in neighborhoods that have a stronger tax base, for example, if I understood that correctly. So hoping you guys could just touch on how do you mitigate bias in the data models?
I'll just start in kind of thinking about this in terms of why might cities have data that is not necessarily representative of the entire system. And so, for example, when we are building a statistical model and trying to predict service line materials, oftentimes utilities will have some records of verified or recently inspected service line materials that they know the material of because they did certain projects in the area. They did road paving work. There's been a focus on economic development. So they've put investment into certain communities. Oftentimes when there's a new home being built or work is being done, that might be another time when a permit is pulled and they get new data in that way. But this stuff does not happen at a random set across the system in the sense that you could extrapolate from what this data is to the entire system, which means that we need to do work to correct or at least explore the possibility that there is bias in that data. Jared, I'll let you go from there to talk about what we do.
Yeah, so exactly what Ian said. Sometimes a city says, look, we've got some records. It's expensive to dig. I mean, that's the whole reason we're talking to you, is that it's expensive to dig. Can we dispense with digging anything and just go with what we've got here? And if what they have is representative of the population, then fine, full speed ahead. If it is not, then we are at risk of perpetuating historical environmental injustice, right? Places that have received more infrastructure spending, more work, more attention from government, typically represent a certain kind of people, and other kinds of people are not represented in that category. And so you end up training a model that finds lead in those areas, but not in other areas, which is what precisely we need to avoid, right? So what do? Our first push is we push hard to do at least some representative sampling, even if you're strapped for cash. Really, if you think about this long term, better data means a better model. If you do a few digs up front to find representative data, your models are going to be more accurate, and you're going to spend less time digging where you're not supposed to down the road. So there's that, right? Now the next, so that's like the first, that's like the best thing to do. Anyone that does anything with statistics knows that you want independent and identically distributed data. Like every single theorem in statistics that is useful for anything relies on having a representative data set to learn from, and everything falls apart if you don't. And so that's the first big push. And I would say that we just won't work with someone. I'm not going to work with someone if they're not willing to have this conversation and try to figure this out. Beyond that, there are some sophisticated statistical tools out there to try to debias a model. And the idea is that you will actually attach a weight to every single labeled piece of data and drop that weight down as that if it is overrepresented in the data set. And so you'll say, I'm going to learn from this, but I'm going to learn from this less heavily than other parts that are less represented in the data set. These tools are, I mean, this is kind of an area of active research. And in fact, we're exploring very recent literature here and thinking about how we might even contribute to it. I think this hasn't gotten a ton of attention, I feel like, in machine learning. Mostly because, thank you for the link. Mostly because I think a lot of, the models that get a lot of attention there is a preponderance of training data, and bias isn't really that big a part of it. Like you think about image recognition or self-driving cars, they have no issue. They have just a metric ton of data. It's so much data, and it's all representative. That's not really the same thing as our case, where we have not that much data. But one key difference is that we do have an understanding of the universe that we're working in. So a lot of machine learning companies don't have the whole population that they know that they're trying to learn from. They have some subset, and they're trying to infer some population that's kind of mysterious and nebulous. For us, the city has a list of houses that we're going to make predictions for. And we have all the information about those houses that we need. We have we know the population that we're trying to predict, in other words, which means that we can debias each of the features more precisely than if that was unknown or nebulous, which is like, someone trying to do machine learning on app users, for example, doesn't have that same luxury we do. So it's kind of a special case, but I am excited about the research direction here, where in this case, which is actually a case that is very important for understanding bias and infrastructure in general, has huge implications for for environmental and social justice. We want to kind of move the needle on that and move the conversation forward and give this is where it matters. This is not just theory, but this is a precise example where the applications of this theory is relevant, important, and helpful.
Fantastic. Thank you for your insights there. I dropped a link in the chat, as Jared alluded to here, but so we hosted a chat recently. If you're interested in diving deeper, we called it Bias and AI, Finding and Fixing the Anomalies in Machine Learning Algorithms, with a couple of very experienced machine learning engineers. So I definitely encourage everyone, if you're interested, to check that out. Something that blew me away was they were talking about, again, with mathematical modeling, that there's a trade-off between bias and variance and some different things that we don't have time to get into, but I see Jared nodding his head. So I'll just leave it there and encourage you to go check that out, because a lot of really interesting considerations that I had not thought about at all. It's not as simple as just like getting rid of it. There's a lot of complicated considerations. So definitely be sure to check that out.
And if I could just add to that, oh, go ahead.
Please
Sorry.
do. No,
well, I was just going to say is that this is the danger of bias in machine learning. Okay, this is a very niche subject, right? People don't often. I mean, before I started working at it, I didn't know what a service line was, and I never thought about it. I think most people don't. This is not going to get tons of attention, and it's easy to see how someone could come in and not think about the bias in models, and very just clumsily, I'll say, train a model and then bring that bias into decision making at the infrastructure level, spending millions, billions of dollars, perhaps. This ends up being that's a disaster. Like, frankly, that's a disaster. And playing with these machine learning models without understanding that is, it's playing with fire. It's playing with a loaded gun. You don't do that. It's crucial. It's crucial, absolutely crucial, that you consider this. I mean, it's basic statistics in a way, but I think it gets swept under the rug and ignored. It's inconvenient, frankly, and so don't do that. If you're in that setting, if you're in the setting, like, make sure you think through it, and don't play with matches.
Yeah, and I just posted an article about some scary stats around just the number of business leaders who are actively thinking about different aspects of bias and algorithms and things. So it is scary stuff, or not scary. It represents an opportunity to improve, and that's all good stuff. So
yeah, it's really short. It's one last thing is that it's really short-sighted, and in the end, your models end up being worse anyway.
Yep.
You maybe get the model up and running sooner, but you end up shooting yourself in the foot, honestly.
Yeah.
Ethical data science is good data science. Good data science is ethical data science. You cannot divorce those two things unless you're really trying to hurt people. And if your goal is to hurt people, then yeah, whatever. But
that's a great way to think about it. Well, I want to do this. So we have just a few more minutes. So I'd love to transition. Thank you guys. So this is so awesome. So much to think about here. I want to ask back to Ian here, or I guess for both of you. How can folks who are listening potentially get involved? So I know, Ian, you posted that you have open jobs available. So I'd love if you could just touch on what you're hiring for in this moment, but also more generally, you had mentioned, I think it was an open source project related to surfacing data or something like that. Could you touch on just ways that folks listening, either here or in the recording, how they can get involved
Absolutely.
and
Thanks,
support the
Jacob.
efforts?
Yeah, for sure. So we currently have jobs available in data science, in software engineering, and in product development. And we're at a very exciting time in the growth of BlueConduit, and we would be really excited. And we're looking for great candidates to help us grow the work and grow the mission and grow the impact. So that's what we're doing right now. As part of some projects that we have going forward, there is the development of open source tools and libraries, speaking exactly to what Jared was talking about in terms of tools to help support debiasing in infrastructure data and things like that. So, we don't, the specific details of what that looks like and the engagement are still being fleshed out, but you can follow along with any opportunities on our LinkedIn or our Twitter, where we'll be posting about those, and really trying to continue to foster conversations around this ethical data science and making sure that that when we do generate probabilities or predictions, or when anybody is thinking about using predictive modeling, that they are thinking about it in the right way, in the ethical way.
Fantastic. And Ryan will be dropping the links to the Twitter and LinkedIn, as well as contact information before we hop here. So let's, again, if you have any other questions to sneak in, just please do. But other than that, curious, what's next? So you've got this very exciting project, no shortage of opportunity to scale the operation. What's on deck? What comes next for the BlueConduit team?
So first is the opportunity at hand, and really the need of why we got into this field. So President Biden is proposing an infrastructure bill that has $45 billion directed specifically for lead service line replacement. And so we want to make sure that that work is done and can to support communities and getting those pipes out of the ground as quickly and as efficiently as possible. And beyond that, there are continuing to explore other ways within water, within public health and data science, where we can help support decisions that advance public good. I think we have a lot of ideas around other potential infrastructure questions, or even the presence of pathogens in drinking water systems, anywhere where we can, help generate decision support, translating the data into actionable information that can allow people to make better decisions that benefit everybody.
That's fantastic. So Mark dropped a question here, Ian. So yeah, that's a great question, Mark, just from the business side, asking if you're operating in the black. Like what does the financing side of the project look like?
So as a company, we have not taken on capital yet. So it's just by founder contribution at this point. But we know that given the scale that we're going to need to grow in order to help the number of communities that are going to need our support, we're looking at opportunities to raise as well. And I think one thing about our work that we didn't quite get into, but is part and parcel to everything, is really is making sure that our solutions are as accessible as they can be to communities, even if they don't have the resources to pay for them in full. So working with foundations and other groups to make it more accessible, whether it's through a matching program or even just a grant from a foundation to provide the services to communities that would otherwise not be able to. Because as Jared was saying, if you don't have the right data, you end up paying a lot more in the long term by the number of digs that you're conducting and the amount of money that you're spending and the amount of time that you are taking to do that, which perpetuate the inequities that already have these communities behind the eight ball.
Got it. So just to wrap up, so I want to first of all just say thank you so much to Ian and Jared for sharing all this fantastic information. I mean, I'm pretty blown away I feel like I need to listen to this talk back because I was thinking about the interview and I want to like really process everything. So I'm very excited to kind of moving forward. As I mentioned at the beginning, you know, the Collider is all about learning through doing, and how we can be using applied learning to be solving meaningful challenges and leveling up. So I'm curious, you know, to continue exploring how our community might be able to organize it and really contribute directly to this project. So I'm excited to continue, Ian, exploring, you know, whether it's a water focused tech challenge of some sort or whatever the case may be. I'm very, very excited to continue that conversation with you. I'm also dropping a link. Thank you, Ryan, for dropping the BlueConduit LinkedIn and Twitter links in there. I'm also dropping the link to the Collider website. If you're not already, definitely encourage you to sign up for our e-newsletter and to connect with us. We've got a lot of exciting things in store, more talks like this and about, you know, other things. I linked to the blog before with the talk about AI bias. We have other talks about machine learning and all sorts of good stuff. So definitely do not be a stranger. Yeah, and then just if you have another quick minute, we got one more question here in the chat around main development focus, R Python H20 Kineme? I don't know.
We do Python.
Python.
Pretty much everything's in Python. I think we might have some R code floating around, but I mean, we need a real programming language. I hope no one gets offended by me saying that. And then we have like the development, like the map that Ian shared earlier that's written in JavaScript with React. And then, you know, we do stuff on AWS. If someone wants to know more about the tech stack all the way up, I'm happy to talk about that, but I think we're out of time.
Fantastic.
Feel free to reach out.
One thing I forgot to mention that we'll follow up with in the and Mark is sharing some sort of idea web here. So I don't have it large enough, Mark. But one thing I forgot to mention is that we do also have an active Slack channel where we discuss all sorts of exciting tech stuff. So Ian is in there, and we'll definitely be carrying on the conversation about machine learning and data science and water analytics and all this good stuff. So we'll follow up with that information as well. But we're a couple minutes over. We want to respect your time and give everyone their evenings to relax. So with that, I want to say thank you one last time. And yeah, we'll have the recording available soon for everybody. And we'll talk to you real soon.